Okay, hello everyone. Welcome back to the Wireless channel. My name is Eric Hansok-Ru, and I'm here to present our recent paper that is going to be presented at the 2025 Wireless Communications and Networking Conference, so WCNC, in a couple of weeks. The topic of the paper is on belief propagation-based rotation and translation estimation for rigid body localization. And this presentation will hopefully give you a nice idea about what we have done in this work and hopefully interest you to also our related works as well. So to go ahead into the paper, we will go through the introduction, of course, behind the whole rigid body localization idea and the system model, and we will go through the proposed method, which is dubbed the double Gaussian belief propagation, and then finally some performance analysis against the state of the art. So first of all, this rigid body localization is a recently proposed idea or recently gaining high attention because it can estimate directly the 3D rotation and the translation of a given sensor conformation or an object like a rigid body. And this is different to the classical radar or even ISAC paradigms where you typically just estimate the range, the angle, the bearing, and the Doppler shift in terms of the velocity. But here, we're considering the entire 3D shape, or we call the conformation of this body, which are described by these sensors that are sensor nodes on a rigid body. And we can estimate the actual rotation and the entire translation of this body. So in figure 1, you can see some example. We have this reference frame of a cube with 8 points or 8 sensor nodes. And this transformed rigid body is described with some rotation that will be described further on mathematically, and also this 3D translation. So some applications of this rigid body localization, of course, are in autonomous vehicles where you not only want to estimate the range and the velocity of a car, for example, you also want to know its orientation. And of course, similarly with robotics, Internet of Things, smart factories, and even extended reality applications. The key challenge in realizing rigid body localization is the accurate estimation of the aforementioned two RBLs, rigid body localization parameters, which are the 3D rotation. So actually this corresponds to the three angles in the X, Y, Z axes, and the 3D translation, which also correspond to three variables in the X, Y, and Z translation. So in the end, we actually have six scalar parameters, but we will denote them as two RBL parameters, which are the 3D rotation and the 3D translation. And what we want to achieve is to get the estimation of these two parameters only using the range measurement between the unknown sensor positions at the actual rigid body and some known anchors that are, for example, the base station or a roadside unit or some receiver or transmitter. So of course, other than using this range-based method that I just mentioned, we also have, of course, other classical methods that can both estimate the 3D rotation and translation. For example, one is using this computer vision. Of course, with the video or image, you can, of course, extract by using, for example, machine learning or some value decomposition methods to extract this variables. However, of course, there's still very high complexity, also data intensive, because you have to take all of the information of the video or image, and of course, also have a lot of pre-training information on that. Of course, the methods are very effective, but also then we have the IMU base, so this inertial measurement unit, which can be positioned at the rigid body, and that can estimate directly the acceleration in the rotation values and the translation values. However, of course, this means that all of the rigid body will have to incorporate this hardware by itself, which could also be costly. And for each rigid body, you will have to have multiple IMUs because not only one will be robust enough to errors, and also each of these measurement units require high calibration, and this will be very inefficient, especially if you have a large number of these devices, for example, in Internet of Things or drone management and autonomous vehicles. So what we want to achieve is simply by achieving these estimation of the parameters only using the range measurement, which is very easily obtained and low power and very simply using some cheap hardware as well. So the proposed method, other than so differentiating from the previous two, is estimating the RBL parameters using what we call the double Gaussian belief propagation, as will be described now. So first, to describe the mathematical system model, we have a scenario with a rigid body with n number of sensor nodes. For example, in the figure, we have n number of sensors in a cube in the rigid body in the middle, and we also have m number of anchors. And in this figure, we have illustrated by having a larger room, for example, with each of the corners having a sense or anchor node. So in this case, this is only an illustrative example, but of course, the number of nodes and anchors can be fully generalized. And then we denote each of the sensor as vector C of n, so the nth sensor. And this sensor is composed of three parameters, which are the 3D positions, 3D locations, and the Euclidean space. And then this rotation matrix denoted by Q is a 3 by 3 rotation matrix, which is parameterized by the three angular rotations in the X, Y, Z axes respectively. And then the vector T is also the 3D translation vector in the X, Y, Z axes. So the transformed sensor position, denoted by S of n in the first equation, is given by the multiplication of the 3D rotation matrix with the original position, and then the translation of T. And of course, it is important to note that because a rigid body, the sensor conformation is fixed, the 3D rotation and the 3D translation is applied identically to all of these n number of sensors. So this can be also written in a matrix form, as will be seen later. So we can denote the range measurement at the receiver by this d of tilde, m of n. So the range measurement of the nth sensor at the mth anchor is denoted by this d of tilde, and this is composed of two components. One is the d without the tilde, which is the true measurement, so true distance. So this is given by the Euclidean distance between the anchors and the sensors. And then we have the Gaussian noise, which is denoted by W, and this is having a distribution with noise variance sigma squared of W. Then we also write the squared range measurement, which is the squared of the range measurement described above. And we have the description in equation 1, which can be alternatively written in terms of what we call a composite noise. So simply by rearranging the terms, we can get the form of equation 2, where these variables have been rearranged such that we get the distances, so the estimated distances, and the true anchor positions and the sensor positions on the right side of the equation. And then we can trivially stack all of the observed data at the M nodes, M sensor nodes, into a vector of the stacked composite noise and get the matrix form as in equation 3. We can now denote this by having an effective channel matrix G, which is of M by 4. And we have an added dimension in the estimated vector of x. So the first three elements here are S of n, which is the translation vector. So not the estimation of the sensor position vector. However, we have the fourth element, which is the squared norm of this translation vector. So now we have four values in the vector x. And of course, the latter noise term is the composite noise from the previous slide. So now we have an effective observed data of y, which is composed of the effective channel matrix G, and then an unknown sensor position vector x, and the final composite noise of. And this is a simple linear equation which we aim to solve. First thing we want to reformulate in the system now is this rotation matrix. So this rotation matrix Q, by using some small angle approximation, which is valid for typical rigid body applications, since the estimation phases are so close apart. For example, the estimation points in time are sufficiently close that the angles, the translation and the rotation angles are sufficiently small. Then we can make the approximation in equation 4, which simply approximates the cosine of a given angle to 1 and a sine of a given angle to the actual angle, we can get the rotation matrix in terms of directly the rotation angles respectively in the x, y, and z axis denoted by theta x, theta y, theta z. And we can further vectorize this matrix Q such that we get the gamma plus L of theta. This L is simply this distribution matrix composed of zeros, 1 and -1, that will map the angles to the vectorized vector. And then we also have gamma, which is corresponding to the diagonal of the original matrix Q. So by using this reformulation of the vectorized Q, we can further we can insert this vectorized Q into the original equation of y that we had before, and we can get this corresponding reformulated system model, which now have decoupled the angular information in theta and the translation information in t. So now we have two effective channel composed of h of theta and h of t, which is fully parameterized by the aforementioned small angle approximation mapping matrix L, and also A, which is the vector A is the position of the anchors, and vector C, which is the original conformation matrix of the rigid body. So using these effective matrices, we can now reformulate the system such that we have a bivariate estimation problem. So first is the vector of thetas composed of x, y, z rotation angles, and the vector of t, which is composed of the translation in x, y, z axis. And the goal, of course, is to jointly estimate the angular variables theta and the translation variable t, which is unknown at the receiver, only given the effective observed data and, of course, the composite noise, which we know the full variance for. So we aim to leverage this bivariate Gaussian belief propagation method in order to estimate these two variables. And because bivariate Gaussian belief propagation enables the estimation of two separate variables which have this different distribution, this is possible using some soft interference cancellation method as well. This soft interference cancellation leverages what is called a soft replica. So each iteration of the message passing algorithm, so denoted by lambda here, we aim to remove the interference or the effect of the estimate value theta hat and the t hat. And given the effective channel, we aim to get this interference removed, cancelled symbol denoted by z of tilde. So this z of tilde is, for example, the estimation of required for the estimation of theta m of k, and we have cancelled the soft interference, soft replicas of the all remaining variables, so the other 5 variables from the system. Of course, describing all the message passing rules at this point is not very efficient for the PowerPoint, so we can skip this for the slide, but you can find them in the full paper. But other than that, we present a major problem in realizing this double JBP, which is that the channel powers, so the channel power of the translation, the channel power of the angle is highly imbalanced because of the construction of the reformulation, such that the channel h of t is typically of much higher power in the order of tens to hundreds than the power of h in the angular. And this can be understood as typically the translation is typically much larger in given time than the angular rotation. So this, when we apply the Gaussian belief propagation, we get a very good estimation of the translation because of the high power channel. However, we get a high error for the theta, so the angles. So we proposed not just using a simple bivariate GABP for the estimation of theta and t jointly, but we first perform in stage 1 this aforementioned bivariate GABP. Then, because the estimation of the translation is assumed to be sufficiently high, we can perform an interference cancellation and remove the effect of the translation from this system after the estimation. Then we perform a second single value GABP on the estimation of theta. So this theta now can be performed, the Gaussian belief propagation can be performed without the effect of the high powered of the translation, such that we can get a refined estimation of the angular unknown variables. So in light of that, we finally present some performance analysis. First, the simulation setup that we've leveraged in the paper is using 8 points for both the rigid body and the anchors. So the conformation matrix, which denotes the position of the rigid body shape, is given by the cube. So the same example as before, where each of the cube uh, is positioned at the cube is positioned at the origin, and the length of each edge of the cube is unit of one, such that all of the 8 points are denoted by these columns of the matrix C. And then the anchor conformation is given by the matrix A, which means that the anchors are positioned at a cubic room of length 20 meters. So each of the values, the positions of the anchors are the columns of this matrix A. We also have performed the simulation where the random rotation angles follow a zero mean Gaussian distribution of variance of 10. So the angular variance is 10 degrees to say. And also the translation vector elements, so the translation of rigid body also followed zero mean Gaussian distribution and of 5 meters in this case. So finally, we have some results here. First of all, we compare the results to state-of-the-art rigid body localization methods, also presented in method 3. In this case, we have the estimation is not performed jointly on the translation and the estimate, not performed directly on the translation and the rotation of the rigid body, but first they perform the estimation of the position, the absolute position of the new rigid body, and then the extraction of the translation and the rotation values follow. So this method is different to ours because our method can directly estimate the rotation and the translation without having to do this multi-stage method of first estimating the absolute values. So in figure 3, we see the translation performance against the range error. So the range error is denoted by meters, so from 1 to 10 to the minus 2. And we can see that at all values of the range error, we beat the state-of-the-art method, and we have a superior translation estimation, as also mentioned before, where we have a high channel power, effective channel power during our formulation, such that our estimation for the translation is very, very good. Then secondly, we also have the performance analysis for the rotation. So the angular values of the estimation, of course, we have the same range values, range error values in the x-axis, and the RMSE is given in terms of the degrees of the angles. Here we can see that for lower range errors, so higher range errors, when the range is quite high, the error is quite high, we get the similar performance of the previous performance in the translation, where we get a sufficient performance gain in terms of the angular estimation. However, because we've mentioned that the error variance, when the error variance becomes small, this message passing based method, so this Gaussian belief propagation, we have an error floor appearing and such that we lose slightly at the lower variance in comparison to the state-of-the-art method here. However, we know that this error floors can be mitigated with improved message passing algorithms, so not using the classical raw Gaussian belief propagation, but for example, by using scaled Gaussian belief propagation or weighted Gaussian belief propagation, or also damped Gaussian belief propagation. These methods are some uh, additional modules to the Gaussian belief propagation, which we know that increase complexity, but sufficiently mitigate the error floor at this lower variances. So finally, we have a rigid body localization method, which we presented using an interference cancellation based bivariate Gaussian belief propagation, which enables a direct estimation of the 3D rotation and translation estimation. And then we have seen that this method outperforms the state-of-the-art in both the translation and rotation accuracy, which also has a lower complexity also and post-processing overhead because we don't have to first estimate the positions and then extract using some singular value decomposition methods of the rotation and the translation. However, we saw that we have some error floor appearing at some low noise areas, especially in terms of the rotation estimation, such that we aim to, in the future works, address this by using some improved Gaussian belief propagation methods. And also we should consider the enhancements of the method in various scenarios, not just cubic shapes, for example, but using various different shapes of the rigid body and also different locations of the anchors, for example, if they're only placed in a plane instead of a room, and so on. So thank you very much. That was the presentations, and if you have any questions, I'll be happy to answer them.
Thank you, Eric. Very interesting work. Brings memories of Vladi. I hope he's enjoying his time there at Rice University. I have a question actually. I was thinking as you were talking about that at the end of the day, the key thing here is to do what you say, double, what you mentioned, you refer to as double belief propagation, right? And I
Right.
was thinking that you had this clever idea to approximate the rotation matrices
Mhm.
in a linear form, right? If you could go back
Right.
to that slide. Right. So now what I was thinking is, all right, of course, this will only work if the angles are sufficiently small. But so long as you are tracking rigid body as it's moving around, you could decompose whatever translation and rotation into small composite translations and rotation. So my question is the following. Suppose that you are too late. Yeah? So suppose that the next observation is not
Right.
fast enough and the car has or the body has already rotated too much that this approximation will not work. Um, could we instead uh, further decompose and say, okay, the new position is the position you had last plus
Right.
small deviations in translation and rotation, and then such that what you're really interested in the end is in the composite. Yeah, you
Right.
have the last observation and the rest are just variables. So my question is this: do you think that we could extend this to such a situation where you decompose wider range of motion into a number of added, because that's linear anyway, right? It would always
Exactly.
just be another q times some intermediate position plus x plus t intermediate position, and so on and so forth. So could you address that?
Yes, exactly. So that is actually even not I wouldn't say easier, but the system formulation would be easier in the sense that you can simply concatenate, as you mentioned, simply many rotations on top of each other. So for example, if you have Q1, which is for the first mini frame, then Q2 for the second mini frame,
Mhm.
which we have decomposed. Simply, if you just keep multiplying the Q on top of each other, we get the total full rotation that we want to estimate, right? And that means if we have, let's say the observed value is too late, as you mentioned, and our Q, the full Q cannot be estimated using this small angle approximation. But if we model the Q as three different Qs that are just multiplying each other, then perform this GAVP, I believe that it is possible to do that. So we
Okay.
may have to the message passing rules would have to be, of course, updated correspondingly because now we have that many number of rotation values. So even if you see the equation 5, the thetas would be, theta 1 for the first decomposition frame, theta 2 for the second decomposition frame for each of the axis, right? So I think it is possible as long as we um, reformulate the message passing rules to accommodate the many more variables that we have gained from
Mhm.
this decomposition. Yep.
Okay. Thank you. Anybody else? More questions? Comments? That doesn't seem to be the case. Then thank you very much, Eric. Yeah, and we can conclude and see you next time.
Yep. Maybe one other thing to add is that we have already some extensions of this work in forms of, I think it's already on archive. So maybe if um, anyone is interested, we can also present those as well in the future.
Okay, then I'll put that in the description of the video.
Yep, I think that'd
Thank
be
you once
because
again.
we have
Thank you,
many. Yep.
everybody. Yeah. Ciao.
Yep.
Ciao.
Thank you. Bye. Did you stop it?